Okay. Welcome everybody to the next meeting of Integrability Journal Club. And today I'm very happy to introduce Benjamin Doyon from King's College London, who will tell us about correlation functions of twist fields from hydrodynamics. Please, Benjamin.
Yeah, thanks. So it's a pleasure to give a talk at this very nice seminar series. So yes, I'm going to talk about correlation functions of twist fields from hydro. So actually, Gerard was asking, is it not in hydro? No, it is really from hydrodynamics. So the idea here is to get exact results for correlation functions in many body systems. So here I'm going to talk about quantum systems, but it's quite general, it goes beyond that, from ideas that come from hydrodynamics. So this is the main thing. And here, the correlation functions I'll be discussing, well, in part, are those of particular fields called the twist fields, which are important and interesting in various contexts. But I want to discuss a bit what hydrodynamics tells us about correlation function in general before that, and then get to the twist field. Okay. So yeah, so this is work. I mean, there's a work that we've written just now with my student Giuseppe Vecchio, and some work in collaboration with Giuseppe and with Márton Kormos that is, yeah, hopefully going to be written relatively soon. So, so the main context is very simple. So we have a Hamiltonian, which is infinitely long, and I'm thinking about one dimension here, but a lot of the ideas can be applied to higher dimension as well. And the Hamiltonian admits some conservation laws. So there can be conservation of energy, conservation of a charge, a U1 charge, there's momentum, or whatever conservation laws. Of course, in integrable systems, which are systems that I've been talking about, there are infinitely many such conservation laws. Okay? So here I write in the discrete case, so a conservation law is there's a density and a current where this is a discrete derivative, and the total sum of the densities over all points on the chain is a conserved quantity. And I'm going to talk about just very simple states, just thermal state at non-zero temperature. So this is not vacuum correlation functions, but correlation functions at non-zero temperature. In fact, I could discuss something more general, something called generalized Gibbs ensembles, where all the conserved charges are involved. So I can discuss much more general state, but for simplicity, just consider thermal states. Okay. So what's the problem that we're interested in here is the problem of correlation functions. That is covariance, so connected correlation functions of local observables in finite temperature. Right? Now, it's not just correlation function at separate point in space, but also a separate point in space-time. So I want to discuss dynamical correlation functions. Now, this is a very difficult problem in general, calculating dynamical correlation function. There are all kinds of techniques based on beta ansatz, inverse scattering, form factors that one can hope to use, but it's rather difficult to get, in particular, what happens with these correlation functions at very large scale. So very large distances and very large time. In fact, for very large distances and time equals 0, in the vacuum, not at high temperature, there are quite a lot of results. Okay? The strongest results are based on technical form factors, where you just write essentially a Kelly element expansion and calculate the matrix elements of local observables. But here, this is difficult for two reasons. One is that this is a finite temperature. So the usual form factor expansion, the Kelly element expansion, doesn't quite work. You need to change it. And it's very difficult to get asymptotics from that. And the other is that we're looking at large time, which makes it even more tricky because you need to evolve the operator in time. So this is relatively tricky. And current methods in integrability do not quite, well, some methods nowadays do quite allow to calculate some of these asymptotics, but it's rather recent. And for twist fields, besides the method I'm going to discuss about for interacting models, there are, as far as I understand, no other methods. So it's very difficult to evaluate these large space-time asymptotics. Okay. Now,
can I ask a really silly question? Sorry, I'm probably going to say something silly, but if x and time, if these points become infinitely far apart, doesn't the right-hand side just go to 0?
Yeah. Okay. Sorry. So I should say. So what? Actually, I'm going to come to that. What do we want, right? So what do we want to calculate? So yes, the answer is yes. That goes to 0. Okay. But the point is, how does it go to 0? So okay. If you're, for instance, I mean, typically in the vacuum, if you have a gap at time 0, at large separations, it goes to 0 exponentially. Which exponential? It's controlled by the MSG of the first of the smallest mass particle. This is rather simple, actually, this exponential. Okay. And what I want to discuss is indeed how it goes to 0. And for twist field, it also goes to 0 exponentially, except the exponent is not just the lowest mass of your spectrum, something much more complicated, and I want to get to a formula for that, essentially. Other questions?
Yeah, I have a comment on this in XX. This time and temperature correlation function was calculated, this asymptotics. And asymptotics is kind of non-trivial. It depends on the direction in the xt plane where you go to infinity. It's not just a gap, some integral of some weight. If you want, I can send the reference.
Yeah, so I don't think this was calculated for the sine-Gordon model. I know this was
XX. It was calculated for XX.
Yeah, I know this. I know that. I'm gonna come to the formula there. So you're going out very fast. This for XX was calculated by you, and other people a long time ago, and this exact formula. And what I'm gonna talk is how to recover this formula from hydrodynamics and much more, so we can get the sine-Gordon correlation function as well. Okay. Other questions? So, okay, so this is the thing. So in general, this is difficult. There are some techniques in the XX model, but in integrable interactive models, there are no other techniques as far as I understand as those that I'm going to be describing. Now, the techniques are based on hydrodynamics. So they're not microscopic calculations. They're based on certain assumptions. I mean, there's quite a few calculations, but of course, it's not completely rigorous. And these assumptions are based on hydrodynamic ideas. So what hydrodynamics is kind of wave propagating and this type of thing. Okay, and the formula that you get from hydro in the end can be implemented using the TBA and using what we call nowadays GHD, and give you some formulas you can put on the computer and understand the asymptotics. So I want to get to the XX model that was just discussed about. So indeed, for the XX model, quite a lot is known. Okay. So this is the Hamiltonian of XX, and we're looking at a large space-time asymptotic. I start with a very trivial one, sigma 3 in XX model. Now, XX model can be diagonalized by Jordan linear transformation. It becomes a free fermion, and sigma 3 is just a 4-point function of free fermion. So this is just with theorem calculation, and you get you can get an exact formula and look and do a saddle point analysis essentially to get a large space-time asymptotic. So I'm looking in this ballistic regime, this hyperbolic scaling. You get a 1/t times some formula that depends on the state in which you are. Here, the state is just thermal, so there's a temperature that's there. Okay. Now, this is nice and simple, but the formula that you get for sigma plus sigma minus, which was calculated by Itzhak and Koripin and Stavnov first in 1992, is much more complicated. This one, instead of being an algebraic decay, is an exponential decay. And as was just mentioned, indeed, this exponential decay is not just a mass or something like that. It involves a whole integral that depends on the state. In fact, you can do that not just in thermal state, but in GGE rather simply. Okay? And it depends also where you look in space-time. So if you look at psi is smaller than 4 max psi is x over t. So this is in the time-like regime, then you get this form. If you look in the space-like regime, you get that form. And it also depends on the magnetic field that you put in your model. So there's a magnetic field there. The magnetic field, of course, changes the structure of the spectrum, but actually changes even the asymptotic of this 2-point function in thermal state. So magnetic field tells you, if you have a gap or not. But this is not at 0 temperature. The gap shouldn't matter. But it looks like it changes the formula a little bit. Okay. The formula gets modified a little bit.
I think formula is the same. Because in time like at least first two, right?
Yes, correct. Yeah, the first two. This one you can
because
write that as well here. Yes, correct. Yeah, it's just a small simplification here. It's kind of the same. I could write x minus vt here in both cases. Yeah. Right,
and remove absolute value in the space like.
Yeah. Yes, correct. So yes, correct. If you look at x large positive or something. So okay, so you have so in fact they kind of look the same. But if you have a magnetic field that's greater than 2, as far as we know, so these formula, they were derived initially there in certain regime, and then there's a thesis by G in 1998 that extended the formula a little bit. But in the regime psi greater than 4, which is space-like, and h greater than 2, which is massive, which is gapped, the formula appears a little bit different. In fact, to be completely correct, it's still kind of the same. It's kind of an analytic consideration in magnetic field. But if you want to do the analytic consideration correctly, because all these values, you've got to add this term. Okay? And this formula, as far as I understand, was not explicitly written in the literature, although it is obtainable by the known techniques in the literature. But all of these formulas one can obtain not by asymptotic of Fredholm determinant or by form factor transformation, all that, but by somewhat simple hydrodynamic principles. So this is, these formulas are known and obtainable by the techniques, but this is an illustration or a check, if you wish, that our hydrodynamic principle works. So I'm going to tell you about what these principles are. Okay. So the point is to, in XX model, to reproduce that from hydro. Any questions about this? So as you see, so what you see is somehow a various type. Okay, so you have a various type of behavior depending on the field that you look at, sigma 3 or sigma plus, sigma minus. And another question here is, well, is there a way of understanding what kind of behavior you should expect? Should you expect an algebraic decay or exponential decay? And what properties of the field will affect that? So we don't have full understanding of this, but partial understanding. Okay. So that's kind of another question to be answered here. With that, we can partially understand with hydrodynamic principles. Yeah. So okay, the other thing is, one can with hydrodynamics, hydro is not entirely rigorous, but is rather powerful because you can use a lot of the properties, a lot of the ideas of thermodynamic beta ansatz, and you have control of TBA. Even in interactive model, not just in XX model, which is free Fermion. And so we can do the same in sine-Gordon model. Now, this is a sine-Gordon Hamiltonian. And we can look at coefficient function of vertex operator. This is a natural thing in sine-Gordon model. It turns out, well, this is rather complicated. There's actually quite some work, which I didn't cite here, by Sajdev in particular in the 90s, looking at these things. It turns out that generically, for generic alpha, not for all alpha, for generic alpha in non-zero temperature, one would expect exponential decay as well. And we have a formula for what this F looks like in the exponential.
I mean, by generic alpha, you mean real alpha, correct?
Yes, yes, sure, indeed, yeah. Real alpha and probably not alpha equals beta. So we'll have to check that. So alpha equals beta.
Okay.
Yeah. So, generic real alpha would expect exponential decay. That depends on alpha, and so we have a conjecture for what that F could be, again based on some hydrodynamic ideas. Yeah. So where I'm going to get. Okay. So this is a question. Now we see from this the different coefficient functions have different large time asymptotics, right? So Bogdan was saying, yes, okay, they all decay, they should go to zero. That's correct. Thank you. And they do all go to zero, but it's how they go to zero. So of course, I'd like to have much more of the coefficient function, be the full one, but already how it goes to zero is rather difficult. And I have to say, I think this formula by Itzhak, Kirk, and Slavnos was quite a breakthrough, actually, when it was obtained, because there was nothing else, I think, at that time for coefficient function and temperature, right? So even just how it goes to zero. So we see some monotonic algebraic decay, some oscillating algebraic decay, which is kind of here there's monotonic term and here there's oscillating terms from the saddle point analysis in the symmetry, and some exponential decay. And the question is, well, is it possible to understand these various terms in some fundamental fashion? So the idea is that they are, in fact, general hydro principles that allow you to calculate all of these type of terms that I've shown in these correlators in XX and in sine-Gordon model. I'm not going to discuss the oscillating algebraic stuff, the oscillation in this talk, because I will probably bring me a bit too far. But I discuss this monotonic algebraic and exponential decay. So some general principle to understand where these come from and how we can get exact formulas for these asymptotics. Okay, that's questions.
Is this going to work for more complicated operators?
Yeah, so this is another really good question for what operator. So yes, the answer is yes, except you need to know a little bit you need to know something about the operators, right? When you see an operator, you need to have some characterization of this operator, essentially. So within the Hydro description, there's a way of characterizing the operator. And so we can do the calculation in an XX model and in sine, for sigma 3, sigma plus, and all that, and for other operators in the XX model easily, of course. And for sine-Gordon, well, not all operators we have the full characterization, but it's only the vertex operator, yes. So that's operator dependent, yeah. So, yeah. Other questions?
Thanks.
Yeah. Okay. So the first thing I want to talk about is the trivial bit. I mean, the non-trivial bit is that, but I want to talk about this trivial bit. That is the trivial bit. I think there is a mic on. Yeah. There is a quite well-known principle in hydrodynamics called the Boltzmann-Gibbs principle. It's been, it's known for quite some time. It was applied, of course, historically in systems that have natural hydrodynamic description like gases of particles, but actually it can be applied to quantum spin chains as well, or to sine-Gordon model or whatever. Okay. So this is the principle of the hydrodynamic projections. So what it says, it's very simple. It says that it's not quite limit, but as x and t is large. Okay. In the ballistic scaling, the correlation function of two local observables should be obtained by projecting these observables onto conserved densities, whatever the conserved densities are in your model. Okay, so this is kind of my little picture for what's happening. The A is kind of modifying the state somewhere. You have a thermal state, and then you put an observable. It kind of makes some little waves. Putting an observable is like modifying the state a little bit from the point of view of linear response. And these little waves travel, and then B kind of observes it later on in time at some other point in space. And if there's a wave that reaches it, then there's a correlation. So the leading correlation at large space-time, leading algebraic correlation large space-time, is expected to be obtained by considering correlations coming from waves that connect one observables to another observables. What are these waves? Like sound waves. What connects the string that produce my voice and your ear or whatever, the microphone and all that, these are sound waves. So this is what gives the strongest correlation at large space-time. Right? It's a general principle. In fact, you can write a bit of mathematics for that. You don't need to think about kind of sound wave and all that. So if you calculate a two-point function, let me actually calculate the Fourier transform of this two-point function, e to the ikx, so at momentum k. Well, you can obtain a formula for the large space-time asymptotic of that, which corresponds to small k and large t. Right? And that formula is purely from hydrodynamics, model independent, and allows you to calculate this large space-time asymptotic. Okay. What's the formula? Well, it's relatively simple. So you have this two-point function, which is space integrated. If you put k equals 0, it's just a total two-point function. And if you know all the conserved charges of your model, you can form this matrix, which is called the static correlation matrix, which just take the space integrated space sum two-point function of conserved densities. This is a big matrix in integrable model. In non-integrable model, it's just say 3x3 matrix or something like that. Okay. And CIJM with the upper index of the inverse, and then the formula, the Hydro projection formula, tells you that if you take the limit when k equals 0 and t goes to infinity of that Fourier transform two-point function, you can calculate exactly by projecting A onto the conserved quantities and then calculating the two-point function of conserved densities and then projecting it back onto B. Okay? So there's a sum of all the indices. The indices are just all the conserved charges available in your model, integrable or not. Okay? And this is kind of an inner product. It's like a projection. So A projected over Qi, you take the inverse matrix there to have the right normalization, and then you put this two-point function of conserved density in the middle. Right? So this is supposed to be an exact formula. In fact, it can be proven rigorously in quantum spin chains in 1D, where you define the limit in appropriate fashion. Right? So
this somehow feels, sorry, Benjamin, it feels a little bit like it's kind of that there's a weakly coupled perturbative description.
It is not weakly coupled. This is strongly coupled. What is weak here, what this corresponds to is a linear response. So this is the small parameter is the linear response parameter. So it's like hydrodynamics is complicated with the full thing. You just describe propagation of waves. So you have to construct your wave equations now that, but it is strongly coupled. And the non-trivial bit is you have to know what the concept of quantity
strongly coupled setting. I don't even know what a wave would be.
Yeah, well, this is it. The concept of quantities will tell you what the waves are. This tells you what the waves are. So this is the mathematical formula representing the wave propagating. I mean, wave propagating is just words. I haven't written down the wave equation, but I could write down the wave equations even in strongly coupled, as long as I know the right elements of the strongly coupled theory. But these elements might be hard to calculate. For instance, this matrix in a strongly coupled non-integrable model, well, it's obtainable actually from the free energy, but you have to know the free energy, which maybe you don't know, right? Which is kind of maybe a complicated quantity, right? So there's some data which you have to know, which is complicated. But once you know it, then that. So there's a reduction of number of degrees of freedom. You just have to know restricted amount of data, and then you can make predictions. Yeah, and integral models, we know all the data. So that's okay. So basically, this.
Can I ask some general physical question about physics? So.
Yeah.
So microscopically, for example, the systems like chaotic systems and integrable systems are very, very different. Yes.
Yes.
But hydrodynamics, you want to say, so it will be qualitatively.
So they are very different. The phenomenology is very different, but all the hydrodynamic principles can be applied independently. In fact, this is very interesting. So this formula is correct for any one-dimensional quantum chain with short-range interaction. So integrable or not, trivial or not, even if your spins don't even interact or whatever, there's always a formula. What changes is, well, what are these QI, these conserved quantities? For integrable models, there are infinitely many. For a chaotic model, maybe there's just one, the energy, right, in quantum chain, or something like that. And what are their overlap in the state, in the thermal state that you're looking at? But so formally, same formula. But in particular applications to the models, very much depends if it's chaotic or integrable, or otherwise, or something else.
If I will take extremely simple model like just rectangular billiard with rigid particles, there will be hydrodynamic behavior also.
Yeah. Yes, there will be. So indeed, yeah, there will be a hydro description. There is a hydro description for everything. Hydro is like the old way of hydro, Navier-Stokes equation. No, it's just chaotic systems, right? But the general viewpoint on hydro.
Ben, just to appreciate the formula a bit more. So it looks like just a completeness relation inserted a couple of times. So it doesn't go beyond that at this point, or?
So it is completeness, but note that you don't overlap over all the possible observables available in the theory, just the conserved densities. So it's a completeness, but in a reduced space. So what it says is that, well, actually, you can project, it's a projection formula. You can project these observables on the space of conserved densities, and that gives you the correct limit. So then once you project, it's just a completeness.
But then, so those states which you neglected, kind of, are they just decaying faster?
Yes, correct. They are expected to be decaying faster, and then in principle you can get the corrections to that by considering
because those which you keep, they're already decaying, right? So they should decay what they
correct. Yeah, these are already decaying, but when you write it in terms of Fourier transform and the limit, the limit exists. This is finite. That took care of the 1/t decay, if you wish.
But what controls kind of difference on how faster those neglected modes decay?
Yeah, so that's a good question. I mean, and to be honest, I don't know right now. So I don't know what controls exactly. So
like
what will be
temperature or?
Well, yes, sure. That will be controlled by temperature, by of course, many aspects of the state, which observable you look at. But what is the mathematical object that will tell you what the decay? This I don't know. Yeah, for now I don't know. How it would work. Yes. And actually, so this is, in principle, also in any dimension, there's a formula like that, which we also have proof, in fact, in lattice models.
But this other modes, do they have another functional dependence, or it is just a level of parameters, or functional dependence itself is different for decaying?
Yeah, so that's a function of kt. Kt is held fixed here. So it's like, this is your ballistic scaling. And what we're saying is that the leading asymptotic is given by that, and the sub-leading terms, will be non-trivial function, not just of kt, of k and t, meaning kt and then 1/t or something like that. You can probably organize it as a powers of t, sub-powers of t, and then functions of kt there. But I don't know the full theory of that yet. So this is not quite known, yeah. So yeah, other questions?
Excuse me, this regime which you use as in thermodynamics, what is the translation of this if you back to your original model you show us, this XX model?
Yes.
What is the interpretation of this limit? Is a low energy limit, as I see here. So can you simply?
It's a large space-time. Okay, so let me skip a bit. I wanted to get to that will explain. I think that answers your question. So very explicitly, what we're doing is 2-point function A and B. Okay, x is on the chain, and t is time evolution. And what you are doing, what's the limit precisely that you're looking at? What's the asymptotic precisely? So because in the formula that I wrote, there was a Fourier transform, there's kind of a bit of averaging over space that happens. And in fact, the precise formula should have an average over time. So in fact, you can rewrite this by averaging over so-called fluid cell. So you take your operator, average over a space-time fluid cell around xt, around Lx, Lt, a fluid cell of length r. L is the scale at which you look to coefficient function. Then you take the limit where L is much greater than R and both tend to infinity. And in that limit, it is expected that this thing decays like 1/L times something that does not depend on R, as long as R is large enough, and that's finite. That's given by, but it's not necessarily finite, but it's actually a generalized function, it's a delta function of x and t, and it's given by that. This is kind of inverse Fourier transform of what I've just written. Okay. That's the limit. That you can kind of put on a computer, try and see if it works.
Benjamin, I have a stupid question about notation. So your delta function has index n and
yes.
j. Is this like Kronecker delta multiplied by Dirac delta function?
No, sorry. This is a good question. This is my little notation. This is delta function of a matrix. So to be understood by diagonalizing the matrix, and then take delta function of the eigenvalue.
Thank you for explanation. Thank you.
Yeah. So this is really a matrix thing, and that corresponds to the propagation of the hydromoles. So A is a particular matrix evaluated by differentiating the current in a GGE with respect to the densities in the GGE. So that's so-called flux Jacobian. Tells you how the fluxes depend on the densities. So it's a matrix of the dimension of number of conserved quantities. And you put that in there, and that tells you about the large time asymptotic of this fluid cell average 2-point function, in principle, according to the theory. Yeah. So other questions? So that's kind of the standard theory, let's say, that you can in principle apply to every local operator A and B, as long as you know it's a conserved quantities and these overlaps. Now, if you, in general, the physics that it represents is the physics of propagation of waves, wave propagating at velocities which are in the spectrum of A, because you have this delta function there. Okay? Now, A is a matrix that can be difficult to calculate, right? You have to know the exact average currents and the exact average densities in your many-body model. And that, if it's iterating, it's difficult to calculate. But if you have it, then you have this formula. Okay? In integrable models, you have it. You have everything. Okay, so this formula can be written in integral models. C is known from thermodynamic Bertin-Zatz. A is known from generalized hydrodynamics. These are all integral kernel, integral operator. And this overlap is just obtained by differentiating the average of your observable in a GGE. So that's the data you need to know. The average of observables in GGEs. And once you have that, you put in there And that, for instance, for just the conserved densities, this is the formula that you get in the notation of the thermodynamic Bethe ansatz. So this is my notation for the density of Bethe roots. That would be the ratio of density of Bethe roots over density of states, so the occupation function. That's the effective velocity coming from generalized hydrodynamics. And these are the TBA dressings of one particle eigenvalues, hi of k, of the conserved quantities corresponding to these conserved densities. So all the data you need to have is from thermodynamics. Once you have it, you have an explicit formula for two-point function at large scales. Questions about this? This is being checked, but this is relatively simple, right? For conserved densities. For instance, sigma 3 is itself a conserved density. So we can do that in the XX model, right? So XX model, and we have, there's a Jordan linear transformation that makes it into a Framions, sigma minus, sigma plus are given by this. Sigma 3 is just, number operator of Framions. And then your Hamiltonian becomes a free fermion. In fact, there are two sectors, but I'm not going to go into details of the sectors, right? If you go in the large n limit, then you do simply Fourier transform, and you from that you see that your energies have a particular form. And in the XX model, you can explicitly construct the conserved quantities. Essentially, you can take them as the occupation function, the number of fermion, number operator. That tells you that the spectrum, effective velocity, are just the derivative of the energy for sine k. And if you just use you can easily evaluate that these overlap between sigma 3 and any qk, which has all these C dagger kck, essentially. It's just a free Fermion calculation. Okay. What you see, of course, is that for sigma 3, the overlap is non-zero. It's something. For sigma plus and minus, the overlap is 0. The sigma plus, sigma minus, they contain a fermion there. So just by fermion number conservation, the overlap is 0. So that means that when you apply the general formula for sigma 2, sigma 3, you get something non-zero and you get the right thing. But for sigma plus, sigma minus, you get 0. Okay. So what we find is that this nice, very general formula, Boltzmann-Gibbs principle, gives you the correct asymptotic at large time, the correct algebraic decay at large space-time, except that sometimes it gives 0, and so it's not very useful. But when it gives non-zero, it gives something useful, and it produces the right thing that you could have computed from saddle point analysis. Okay. So essentially, this hydrodynamic formula is a more involved way, so to speak, more general way of doing saddle point analysis, but valid for any interacting model as long as you know the right quantities. Okay. But so importantly, we see that for sigma plus, sigma minus, we get 0 from this general Boltzmann-Gibbs principle. So we need a new principle, and this new principle has to do with the twist field, which is the thing I'm going to come to. Any questions about this?
Yes, quick question. So, does your hydrodynamic also allow for correct prefactor?
So this prefactor here, yes. So hydro tells you, so 2 over pi square root of something blah, blah, blah. This is what hydro tells you. So this 2 over pi square root of and some, that's the overlap. It exactly gives you that factor. Yeah.
Mm-hmm. And also in interacting, also there is no problem, at least for this. Okay, great. So
thanks. Indeed, interacting. So this prefactor basically becomes so it's essentially that. It's essentially that. So it becomes a TBA quantity, that prefactor. That's what Hydro tell you, that the prefactor is a TBA quantity. So you have to calculate things in thermodynamic Bethe ansatz to get it. Other questions? So there was a question about the physics. Of course, the physics is very different in chaotic system and integrable models. In chaotic system, you would expect the spectrum of your A to be discrete. So you just have few directions where you get non-zero algebraic correlation. Otherwise, you get exponential. While in integrable model, because of the continuous spectrum, you have a lot of hydrodynamic models. Essentially, you have infinitely many sound velocities. Then you have an algebraic decay everywhere in space-time as a continuum. And that's why when you do a sigma 2 calculation, you get a 1 over t times something that depends on the ray at which you look at everywhere. So this is specific to integrability. You wouldn't expect that in a chaotic system. Instead, chaotic system, you would expect something non-trivial on certain rays and otherwise decaying. Okay. Okay, so you can also there's also a formula for hydro projection that allows you to get the oscillatory term, but I'm not going to get over into that. Now you can also try to apply the same thing in the sine-Gordon model. Is that question? Yeah, sine-Gordon model. Now this is very interesting. So you can look at various type of field, but here you can consider this exponential field. Now this exponential field is the I alpha phi. So well, in sine-Gordon model, there is some kind of a gauge invariance. So there's a non-compact symmetry, which is symmetry by where you add the field phi a quantity 2 pi over beta or n 2 pi over beta for any n for any n in z, any integer. So this is a non-compact symmetry, and that means that certain correlation functions are going to be 0. So for instance, the conserved charges themselves, they can be constructed in sine-Gordon. They're a bit more difficult to write explicitly, but we know that they are invariant under this symmetry. So if I look at a vertex operator, this vertex operator generically for generic alpha, real alpha, is not invariant under this symmetry. And so I would expect this hydrodynamic overlap with conserved quantities to be 0. Okay. And so that means that e to the alpha, again, like sigma plus, sigma minus in XXZ, in XX model has 0 overlap over the conserved quantities. And so from the point of view of algebraic decay, these 2-point functions should be 0. That's in accordance with the results of its codependence enough, which says that it decays actually exponentially. But then the question is then, okay, can we go further and can we get this exponential decay?
You have a typo in this latest formula. The argument for the second phi should be 0, 0, right?
0, sorry, this should be 0, 0. Yeah, thank you. Yeah. So indeed, so this kind of simple principle tells us that there's no algebraic decay. Now, how do we get to this exponential decay? So we have to use other hydrodynamic principles. So what are the other hydro principles that we're using? So it's the main principle is about large-scale fluctuations. So what we do is the following. In both cases, sigma plus, sigma minus, and e to the I alpha phi, these are actually twist fields. So let me discuss what I mean by a twist field here in the context of a hydro description of the model. Okay. So remember that we have these conserved densities and conserved currents. Now, they satisfy the equation dtq plus dxg equals 0. So it's always possible to formally solve this equation by introducing some kind of height field, phi I, okay? Such that q is dx phi and j is dt phi. Now, phi is just defined as the integral of q, nothing else, right? It's not so complicated. But because this is a conservation law, that means that that integral over space of q, if you think of it as integral over two currents, is actually path independent. So if I calculate e to the lambda phi xt minus phi 0, 0, close parenthesis here, I can write that as e to the lambda, the integral from 0, 0 to xt of the perpendicular to current. And that integral does not depend on the path that I'm taking. So in fact, you can think of that as something that just depends on the endpoints. Doesn't depend on path, just depends on the endpoints. And the idea of the twist field is that because this just depends on the endpoints, then that represents a 2-point function of some fields at the endpoints, and these fields are the twist fields. So the twist fields are just exponential of these height field introduced from the conservation laws. That's more or less what it is. Okay. This can also be written in the XX chain, where you have a discrete space where that integral of the two current is an integral over time and a sum over x, and it's also path independent. You can integrate over time at various points in space or sum over x in various shapes, and you get the same thing. Okay. So these are the objects for which there is a hydrodynamic theory. Okay. So exponential of integral of two currents, which are kind of twist field. Now, how do they connect with the sigma plus sigma minus of the XX model? Well, this is by the Jordan-Wigner transformation. Essentially, what you get is the Jordan-Wigner string. So more precisely, sigma plus by the Jordan-Wigner transformation is a dagger and an exponential I pi, a sum of a dagger A. This a dagger A is just a conserved Framion density. So this is the conserved density. So this is exponential I pi sum from 0 to x minus 1 of a conserved density. So it looks like we have a phi 0. In fact, we have a phi 0 xt minus phi 0 0 0 0 t. We start at 0 here, right? So it's actually a kind of a product of two twist field. But in fact, as it turns out, if you calculate the 2-point function, sigma plus, sigma minus, one can argue that the Jordan-Wigner string transforms into one of these space-time integral of two currents. So it is exactly e to the I pi of a product of vertex operator, which I just write. It's a product of vertex operator, which I write as e to the I pi phi of xt phi 0, 0. And it's which phi is the phi 0 because it corresponds to that conserved density, which is just the Framion density, one of the conserved charges available in the model. Okay. So the Jordan-Wigner string in a space-time two-point function can be rewritten, at least for the leading large space-time asymptotics, as a product of vertex operator up to these fermions at the boundary, some boundary fermions there. So that's why this theory of vertex operators of twist fields in hydrodynamics is useful for this two-point function, XX model. So any questions about this?
So phi is a twist field. This phi sub 0 is the twist field. Is this your definition?
Yeah, sorry, my definition is this. E to the phi is a twist field. Sorry.
Thank you.
Yeah. And so e to the I pi phi is one twist field, and e to the minus I pi phi is the other twist field, and I've put them together in the exponential here.
So what about phi I? Is a simple formula like this?
Yeah, so for the other conserved quantities, one can write, other, for the free Framion model, there are simple formula for qi, and so you can easily construct the other twist fields indeed, and Gaussian functions of the other twist field. But the one that is physically relevant for sigma plus, sigma minus is phi 0 in that case. So I'm just concentrating on that really. Another question.
So difference with the exact Jordan string mapping is what is in time dependence, because
yeah. Time dependent. So if you like this is exact. Of course, you can write this as function of t. So this becomes, there's a t there, there's a t there. In fact, the time evolution change sector, right? E to the IHT on the left and on the right is different Hamiltonian, right?
So originally you have like 4 vertices, like 2 of them is just time evolution is Hamiltonian, which is also like quadratic in fermions.
Yes.
But then you replace just with 2. And that's kind of approximation.
That's an approximation. So you use the fact that you have a change of sector on the left and right there because sigma plus changes number of fermions, and that change of sector brings you an integral of a current over time, and then you can put that back in the exponential, and in the end you get only 2. Yeah, it doesn't depend anymore on where you started the Jordan-Wigner string, so you can get rid of that. That's by the independent invariance on the change of path essentially.
Yeah, okay, there are many questions, and actually it is the moment, looks as a natural moment for coffee break, so maybe we will pause for a few minutes.
Yeah, so can I ask, how much time do I actually have? Or?
Well, coffee break around 10 minutes and then 20 or so.
Okay, yeah, because I don't have much more than 20 minutes.
Can I make a philosophical comment?
Yeah.
Lecture, but I'm not so sure. So, I mean, as for time and temperature dependent correlation function, we also calculated them in the electron gas. In the chat, I sent the link. And those electron gas are solvable by hierarchical beta ansatz. So it would be interesting to develop your technique for kind of I guess it will be 2 hydrodynamics interacting with one another.
Yeah. Thanks a lot. Yeah, I'll have a look. Yeah, that would be really interesting. Certainly. That's
a link. You see the link in
yeah, I see the link. Thanks a lot. That's excellent.
I'll try to come after. Okay. Thank you.
Thank you very much for coming. Yeah. So thanks for everybody who are still there. So yeah. So this is the idea that you can rewrite this 2-point function sigma plus sigma minus in terms of product of twist fields, essentially, which exponential of difference of height fields at different points. Height fields being defined from the hydrodynamic perspective as integration of densities and currents. Okay. So really you rewrite that as an exponential of a space-time Wigner string, where you integrate over space-time your 2 current associated with the Fermion number. Now you can actually do the same in a sine-Gordon model, just to justify a bit further, why this is useful for these models. So in sine-Gordon model, there is the so-called topological charge. So this is, from a sine-Gordon point of view, is nothing else but the difference between phi at infinity and phi at minus infinity, or phi very far in the on the right and very far on the left, which is the integration of the derivative of phi. Now this is, so you can say, well, I can do that for any field and any theory. I mean, what was the use of that? Why do I call that a topological charge in the sine-Gordon model? Well, the main point, the main property it has is that this is actually an extensive charge. And that's because there is this symmetry, right, under addition of 2 pi over beta. In fact, phi is non-compact. More precisely, I should have said it's not quite as it, because phi is non-compact. So that means, for instance, if you look at the difference phi of x minus phi of 0 square, so you look at the variance of that in your thermostat, that will grow like x at large distances. So your phi field is something at 0, but then if you go far away, because there's nothing that really constrains it to lie within something, it can go as far as it wants, because the potential is cos beta phi, it can go very far. It will go very far. And in general, it will scale like x. And when an operator square average scale like x, this is called extensive. And so that difference of field is extensive. And because you go, plus or minus infinity, then it's time independent. I mean, you can, fix the asymptotics and all that. So it's a constant charge. Okay, so that's the basic thing, that you have a non-compact field, and whenever you have a compact field, you can do the same construction. So, so you can identify phi 0, this height field, just with that sine-Gordon field. The sine-Gordon field is itself a height field, naturally. Yeah. Oh, something important. So, okay, so yeah, so that's the thing. So you can also do that, and then you have access then to the usual vector operator of your sine-Gordon theory by these twist field in hydrodynamic theory. Okay. Now, how do you calculate this? So the point is now we want to calculate that, that thing. So I showed you that it's related to XX model, sigma plus, sigma minus, and to sine-Gordon theory vertex operator. Now we want to have formulas from Hydro to calculate this. So there is a theory which we have called ballistic fluctuation theory, because it sounds very much like macroscopic fluctuation theory, which was very popular and all that. So we can try to kind of steal the name a little bit. So okay, so what it does, it allows you to calculate exactly what average of this kind of exponential, so Jordan-Wigner string or product of twist field, this average of exponential, how it behaves when L is very large, when you scale xt with L. Okay, behaves like L times something. So what is that? Well, the theory is based on something called large deviation theory, which allows you to calculate average of exponential of random variable that scale linearly with some parameter, time, space, or whatever. Okay. Actually, the basic thing you can think of is thermodynamics. If you calculate the average of the exponential of the energy over a large volume, what you get is the exponential of the volume times the free energy. So in thermodynamics, the free energy is essentially that thing. In fact, precisely, if I put t equals 0 in here, so there's no integration of recurrence, it's just a density, all I do is modifying my thermal state by adding to it e to the lambda times the total charge between 0 and Lx. Okay. What does that do? Well, that kind of changes the free energy. So this F is just going to be the difference of free energy at a modified inverse temperature for the charge Qi, so beta I plus lambda, minus the free energy at beta I. So already at t equals 0, from purely thermodynamic thinking, you know that this should go exponentially with a certain F, and that F is the difference of free energy, just free energy. So if you know the free energy, for instance, from thermodynamic beta ansatz, then you have this formula. If you know the free energy in your chaotic system, then you also have the formula for that. So you know how to scale like L. With time non-zero is more complicated. And that object is essentially some dynamical extension of the concept of free energy. Okay? Any questions about this? The point is to calculate this F. So how do you calculate this F? Well, the main idea is a bit technical here, but I come to the result then. The main idea is that if you insert that exponential within the state and normalize your state appropriately, well, you modify your state in a certain way. Suppose I take L to infinity there and insert this. I modify the state, but you get a new state that depends on that lambda. Okay. So if there is no time, the new state would just be the state where beta I has been shifted by lambda. It just changes one of the Lagrange parameters in your GGE. But because there's time integral of the current, it changes a bit more. So when time is non-zero, it changes a bit more. And so what the theory says is that the state you obtain is still a GGE. So it's still independent of time and space, and it's still a GGE with different betas. And what are the betas? Well, they are obtained by solving an equation that know about the x and t that you have there, and which charge that you are using. And the equation is just that the lambda derivative of these betas in your GGE is given by the sign of that matrix. It's a matrix. Take the sign of the matrix from the viewpoint of functions of matrices, and take the element ij. I is what you form the state by, and j is the beta you look at. And so that is a new state, which is obtained by what's called a flow equation. So essentially putting that conserved two current there in some diagonal way, makes a new GGE there, and the GGE is obtained by this formula. Questions about this? So at lambda equals 0, so this is a flow equation with initial condition lambda equals 0 being just the initial state that you're at. So this will be our thermal state. So we have a beta for the energy being something, and now the other betas being 0 or something. Okay? And psi here is x over t, right? So that depends on psi. Okay? So this is a flow, and then the formula for f that we want here is obtained by integrating over that flow. So f is just given by the integration over that flow of t times the average current on that GGE minus x times the average density in that GGE. Now the GGE is along the flow, so it depends on the flow parameter lambda, and also depends on psi, the direction in space-time that you look at. That's the technical formula, right? This is it. This is what we have derived, and that should be valid for any hydrodynamic system, as long as you know what the conserved quantities are, so what the GGE is and all that, so chaotic or integrable or whatever. Okay. In the XX model, if we take for the Fermi number I equals 0, then actually it's very simple. This formula simplifies quite a lot. The flow equation just tells you that your energy, your beta E, your energy in your GGE is modified by something that depends on psi, here written as x and t. Psi is x over t, just lambda times the sine of the x minus tv. And this f0, well, that can be, this integral can be done. And in the end, it becomes an integral over the momenta, x minus tv log of that. This is exactly, of course, what appears in the original formula. So this is the general interpretation from Hydro of that formula that was originally appeared in the paper of again correspondence. So that's the BFT kind of gives you the general context for this, if you wish. Okay. Now, so if you apply it to the sigma plus sigma minus, there's actually another little detail. It's a little detail, but we spend quite a bit of time on that detail actually. So what we have is there's some fermion at the boundaries as well. So there's not just a string, but the fermion is the boundary. It turns out that this factorizes into a two-point function of the fermion in the flow modified state times this exponential of this kind of dynamical free energy.
Benjamin, is factorization exact or some corrections to factorization?
No. This is supposedly, we don't have full proof of that, but we think it is valid from the point of view of exponential behavior.
So you mean that the correction in the right-hand side, the correction will be exponentially small in x and t? That's what you're saying?
So no, what I mean is, so I don't have the full understanding, but what I mean is there may be correction of the type, times t to the power something. So powers of t might be correction there. I don't know. I don't know.
I understand. Thank you.
I hope, I think that it's possible that these t to the power something corrections are not there, that this would be exact at this level, and then it would be plus exponentially small term. I hope so, but I don't have proof of that.
I understand. Thank you.
Yeah. So that's the situation. At least for the leading exponential behavior, we think that this is correct. It's factorization. So okay, so once you have that, then it's a matter of evaluating a two-point function of fermions in the GGE, which we can do. So GGE is a free fermion and all that. We know the exact GGE is represented by this modified energy. It's just a modified energy. Okay. And that F, we know what it is. It's given by this formula, which comes from that ballistic fluctuation theory. Right? So we put that together, and we get exactly these formulas. So we produce exactly everything. So that's the hydro interpretation of formulas that can be obtained by techniques and most that were known essentially. So this extra bit, for instance, comes from this factorized 2-point function of Framions, that little extra bit. And yeah, so it says that for h greater than 2, well, there's an exponential decay for this Fermion 2-point function, while for h smaller than 2, there's no exponential decay for this Fermion 2-point function. And it's interesting because you may think, well, a Fermion 2-point function in a thermal state certainly decays exponentially. And yeah, so it can be expected to decay exponentially, but this is a modified thermal state by lambda, and this lambda modification is a bit weird because it adds lambda sine x, and lambda is I pi, so it's imaginary. That changes, that make it kind of bosonic distribution to the Fermi. That changes a bit the structure, and that's why in some region there's no exponential decay, and in other region there is. So there are zeros of the filling fraction that are pose as a filling fraction that are on the real axis in certain regime, and other regimes they are away from the real axis in K space. Okay, questions about this? So that's the thing. Now you can, so we did numerics to check. Of course, we did much more numerics than that actually, to check that our formulas are correct, because there's quite a few steps where we don't have full control, of course, of the corrections nowadays, and it works nicely, very well. This is the case for space-like region, exponential minus x over xi, so at time 0 for various temperature, and that works super well for various magnetic field. So these are the exact exponents that we get. Okay, so now we can go to the sine-Gordon. I will finish there, and sine-Gordon is much more complicated. I could do a whole technical talk about this. TBE of sine-Gordon is more complicated than all that. The sine-Gordon model is a non-diagonal theory generically for generic parameters. So if you do the TBA, you need to diagonalize the TBA, and then you get the magnons and all that. There's a recent paper that did the full construction, at least from the point of view of GHD, where all the formulas that we wanted actually are there. So in general, you're going to have doublets of which I call theta, which are a form of the rapidity, it's a relativistic theory, and the type of particle, the magnons, the original particle, and all that. So in general, because when you diagonalize, you will have infinitely many type of particles. So you have infinitely many couple integral equation in your TBA. There are various ways of making these equations finite, and there's experts in the virtual room on this, how to deal with this TBA equation. And technically that is interesting, but for now we just considered in our work the values of beta for which this the family of possible type of particles after diagonalization of TBA truncates to a finite number. And we just took p equals 3, or p equals 2, I think. No, wait. So something simple. So you have some TBA equation. In any case, the formula is general. The formula from GHD is general. It doesn't matter how many type of particles you have and all that. You just have to sum over all of that. When you have infinitely many type, maybe it's not useful because it's too complicated. At least for finite number of types, it's useful. But in a way, it's general. And the way that it looks like is it just generalizes. Basically, if I come back, it generalizes that type of thing. In fact, kind of that type of thing to the interacting case. So what do you have in the interacting case? Well, there is a pseudo energy, which replaces your energy, and that function, it doesn't matter too much what it is here. This is a self-consistent set of equation. So the function this is the function that satisfies the differential equation for the flow. So you have here a differential equation for lambda. Eventually, you want to evaluate that as lambda equals I pi or I alpha. Lambda equals I alpha, because you want this vertex operator. Okay, so that's okay. Here it's written, not necessarily for lambda real or complex, for generic lambda. And the differential equation tells you that you should take the sine of x minus tvf. This is the effective velocity that is evaluated on that state that depends on this pseudo energy. That's why it has all these dependence. And you multiply by the dressed of the function that evaluates the U1 charge of the particle theta. What's the U1 charge? Well, depending, which magnon you're looking at and all that. So there's some U1 charge, some formula for that. So 1 or minus 1 or 0, that will be this, right? And you dress it with respect to the TBE dressing, with respect to the state in which you are, the state at lambda xi. It's a complicated, relatively complicated, but it can be put in a computer and solved, this differential equation, with initial condition given by the absolute energy for the thermal state. And once you have that, you put that in F0. So this is the F that describes the leading exponential decay of this vertex supported 2-point function. And now it's just a matter of integrating over theta. Again, there's some sine, there's some log. This is like the difference of free energies again, but with the pseudo energy that involves there instead of the real energy. And there's some extra term that's a bit complicated that depends if your effective velocity is equal to x over t, which is xi here, or not. So whenever it's equal, you add a term and you have to calculate this term. So there's some formula. This second term is not there in the XX model because the effective does not depend on the state, doesn't depend on lambda, but is there in general, we think. And what you get in the end then is a integral differential set of equations. So differential equation with integral equation with undressing, which can in principle be solved numerically. So it's not a very explicit formula, of course, but it's still a formula, and you can get a curve. And fortunately, I didn't have time to get the curve that we have obtained, but there's a curve as function of psi for this that you can get. And now the point is to try to verify against numerical calculation, and we are in the process of seeing if this can be done. So this is the result for the sine-Gordon model, with a few details being hidden, but essentially it's that kind of formula that one has to calculate, to solve. So it's a generalization of the original formula of it's again Kormos and Slavnov that involves the interaction. Yeah.
Thank you.
Yeah. Any question?
I mean, I have a stupid question. So the definition of this lambda asterisk with a low asterisk, this is the lowest second line under the sum. What's the definition?
Yeah,
that's the definition, right?
Yeah, correct. So this lambda so low asterisk is the one that solves the equation where effective velocity at that lambda is equal to the ray x over t.
I understand. Thank you.
And so, and it also must satisfy the condition of being between 0 and lambda. It's kind of some additional contribution you get as you go along the flow. You get these additional contribution whenever there's an effective velocity. There's a mode, a fluid mode that exactly agrees with the ray that you're looking at. Then that gives some kind of extra fluctuation, extra correlation that you have to take into account somehow.
Interesting.
Yeah.
There was another question. Somebody else was talking, right?
Yeah, so very naive question. So for XX, okay, so second term was absent, and the sign, actually it was really handy because it's basically made you absolute value, right?
Yes.
So then you guarantee that you decay.
Yes.
Now, how do you see here that your function is negative actually?
Yeah, it's not completely trivial I have to say, to be honest. Numerically, it looks like it's fine. It has the right sign. But if you don't do the numerics correctly, of course, it can go to the wrong sign. So it's a bit delicate. So I don't know. Good question. Okay. Sorry, I don't know. Okay. Yeah, I don't know. There's a whole theta integral and all that. So yeah.
Yeah, because it's really dangerous. So not to get like exponentially increasing.
Yeah, totally. I agree. Yeah. So I should say, so this formula is being verified not for the sine-Gordon model, but for a classical model called the hard-rod model, where we look at the vertex operator, the kind of twist field for the energy, so the exponential of the energy transfer. Also, I think we also looked at the number of particle transfer and all that. So, and we checked that, we calculated from this, actually, the first few cumulants, and they worked. So from numerical simulation, they work for this very simple model.
All right. Also for t equals 0, I think it should be doable by the methods of this quantum transfer matrix, right? Because you need only.
Yes, I think so. Yes, I agree. Yes.
So it would be nice to compare with.
Correct. Yeah, I agree. So for t equals 0, that should simplify to a difference of TBA free energy, and quantum transfer matrix will give you that. Yeah, indeed.
Fantastic. Good. Thanks.
Yeah, very good point, actually. Other questions?
So the second term depends on T only through this X lambda star thing.
Yes. Yeah. Yes.
Hi, I'm sorry. Can I have a question? In the first part of the presentation, you stress sometimes that it is important that your chain is short range.
Yes.
Right?
Yes.
What do you think? Do you think that there are huge obstructions for long-range systems?
So this is a good point. So certainly there is no obstruction if your interaction decays exponentially with distance. That's okay.
Yeah, okay,
but this is still
of course it's somehow trivial. I mean, I was thinking about algebraic decay.
Algebraic decay, and I think there are quite some differences in that case because so the whole theory really is based on the idea that the decay of the interaction is stronger than any power law. So you've got to have that, otherwise you have various things that can happen. Now, in particular here, for instance, for deriving this theory, you look at the multi-point correlation function. You've got to make sure that they are integrable and all that. And once you start having power law decay, yes, I don't know what's going to happen. So, okay, so I mean the answer, of course, is I don't know, but intuition is probably important. So I suspect that the hydrodynamic theory that I'm using will change quite a bit if you have power law decay. Probably hydro projections will be different, and probably this ballistic fluctuation theory also will be affected.
I mean, because probably in certain cases, I don't know, in the dynamics is different, but at least in certain, let's say, classical model, what happens is that typically if the power law is sufficiently high, the exponent, then there is some sort of irrelevance from a renormalization group point of view.
Yeah, no, you're right. Yeah, you're right. So yes, I don't know. Maybe it's also still the case in dynamics. Maybe yes.
I see. Thank you.
Yes. Thanks. Yeah, so that's all I wanted to say. So conclusion, yeah, so if the theory is in principle applicable to other fields such as exponential of the displacements in total model. So any field that is non-compact, right? When you have a crystal, you break the translation symmetry. Well, there's a translation symmetry that and that is non-compact, and then so the point that's there and the point that's there might be the separation might be varying quite a lot. So you can get access to that. In principle, you can get access to the fundamental field of the Lieb-Vinegar model as well. Although it's a bit more tricky, so I'm not sure. And there was, the paper that was mentioned, or that Vladimir mentioned, that maybe that be possible to apply the theory. So we're looking now into, can we apply the theory in other situations as well? In principle, the theory can also be used to study the growth of observables after quantum quenches. Because you can, for twist field, you can relate that to 2-point functions in time direction, in fact. So there's a connection between growth of a 1-point function after quantum quench and 2-point function in real time in the GGE. So in principle, I can give access to that. That would be interesting. For instance, in the context of entanglement entropy, where you have 2-point functions of twist field in entanglement entropy, and perhaps this can give access to the growth of entanglement entropy that has been observed numerically and calculated in various ways. So we hope to be able to get exact results there, maybe, for interacting models. So this function is called also full counting statistics in mesoscopic physics. So it's it's related to fluctuations and all that. And finally, the theory that I presented with the flow and all this, I mean, there are other ways, in fact, of calculating fluctuations in time. There's something called macroscopic fluctuation theory, which has been developed for diffusive models, non-integrable. And we're trying to see if we could do something for integrable systems here as work in progress. And that might give rise to different formulas, perhaps less complicated than that one for similar quantities. So we're looking into that. And that's all I wanted to say. Thank you for your attention.
Thank you, Benjamin, for very interesting talk. Yeah, there was already many questions.
Yeah.
So, is there something else what people want to ask? Or we can actually stop the recording and proceed. Okay.